So here's a example of a data set where we have ages, so 1, 2, 4, 6, 8, 10, and 11. And then for our y values, we're showing the percent of an adult size brain. So a 1-year-old, their brain would be 30% of that of an adult. A 2-year-old, their brain would be 50% the size of an adult brain, and so forth. By the time a child is 11, their brain is about 99% of the size of an adult brain. So we're going to look at this data in a scatter plot and then see if we can come up with a model that will allow us to make some predictions for brain size. So here is my calculator, and I'm going to add in my data: 1, 2, 4, 6, 8, 10, and 11. Those are my x values. And then in column 2, I'll put in the percentages: 30, 50, 78, 88, 92, 95, and 99. So let's look at a scatter plot. So actually, first I want to make sure that I have everything cleared out. Yeah, I'm good. So stat plot, and I want to turn off this second one just in case there was something in there. And go back to plot 1. It's on. I want a scatter plot. My x values are in list 1, my y values are in list 2. I think I'm good to go. So let's see. Let's go to zoom, option 9. So here is the scatter plot. So I'm seeing that the percentages increase rather quickly. So those are when the child is an infant or toddler. So here's age 1, age 2, and age 4. So the brain is developing rapidly, and then it starts to slow down as it's reaching almost the full size of an adult human brain by age 11. So this pattern to me looks like a log pattern. So let's go to our stat menu under calculations and see if we can find a log regression. It is somewhat confusing that there is this logistic here. That's not the option that we want to use. Our only option in the TI-84 is the natural log regression. So this will be a log function with base e. That's what we're going to use. The natural log, our data is in list 1 and list 2. So we come up with an equation in the form y equals a plus b times the natural log of x. And we're actually going to use the values. Let's just round these to whole numbers. We'll say that a is 32 and b is 29 times the natural log of x. And let's see how our model does at making predictions. I'm actually going to make a new table here of x, and these are the predicted y values. So these were the observations. These are going to be predictions. I'm going to do this for the same values, but I'm going to insert a 5 here, and I'll tell you why in just a minute. So 6, 8, 10, and 11, and so let's make the prediction for a 1-year-old. So I'll take the natural log of 1, so the natural log of 1, which is 0, multiply that by 29, you're still going to get 0, and then add 32. Oh, I multiply by 32. Obviously, when you add 32 to 0, you're going to get 32. So let's do the next one. For 2, the natural log of 2 times 29, add 32, and we'll get 52. The natural log of 4 times 29 plus 32, that's 72. And here's the value that I'm adding. So this was not in the original data set. The natural log of 5 times 29 plus 32 is 78.6, so we'll round up to 79. The natural log of 6 times 29 plus 32 is 84. And the natural log of 8 times 29 plus 32 is 92. The natural log of 10 times 29 plus 32 is 99. And lastly, the natural log of 11 times 29 plus 32 is 102. Okay, so here are the predicted percentages. And let's see how those do compared to the observed percentages. 32, okay, so it's a little bit higher. Also, we're a little bit higher here at 52 as opposed to 50. Now we're a little bit under 72 as opposed to 78. There was no observation of a 5-year-old, but we have 84, a little bit under. We're spot on for 8-year-olds, 92 and 92. And then we start to go off again. And in fact, for an 11-year-old, we predict 102, which wouldn't make any sense. You wouldn't have a brain in a young person that's 102% of the size of an adult brain. I think these would max out at 100. But the reason I wanted to include 5 here is to emphasize the reason that we create models is to make predictions to kind of fill in some gaps, or when we cannot make an observation. So I didn't have an observation for year 5, but I can predict that a 5-year-old would have a brain that's 79% of the size of an adult brain. And that's probably going to be a fairly good prediction. If I look at my model relative to the scatter plot, so I'm going to add in here 32 plus 29 times the natural log of x, and go back to my scatter plot, but this time I add the regression line. Yeah, I can see that there's a pretty good fit. This line comes pretty close to my data points throughout. Sometimes the data is a little above the line, sometimes the data point is a little below the line, and we saw that when we compared the predictions to the observations. Again, these were my predictions using the model. These were the observations I used to build the model. So these are ordered pairs that are on the scatter plot, and then this is the line that we're seeing over top of the scatter plot. All right, so I hope that's helpful, and I think that's it for videos on modeling using exponential, quadratic, and logarithmic functions.